Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutwa Sos Ugobela Wemets. So in today's lesson, we're going to be looking at physical sciences on the topic of momentum and impulse. And I'm using a document here by Munyetla Basari Project 2023. So I hope I do not get any copyright strikes from that. This is mainly for just teaching purposes and nothing else. Right. So without any further ado, let's look at these questions, or rather these definitions that we have here. So we have definitions as per DBE examination guidelines 2021 and 2015. So we have the first definition there is velocity. So what is velocity? It says is the rate of change of position, right? And then we also have momentum. This is the product of the object mass and its velocity. So if you happen to forget the definition here, you can just look at the formula. P is for momentum, and then we can see that this is the product of the mass and the velocity. Remember, when you multiply quantities, the resulting answer that you get, we call it a product, right? So the solution that you get from multiplying, we call it a product. Hence, we say momentum is the product of the object mass and its velocity. Then we have Newton's second law in terms of momentum. It says the net force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force, right? So as we move along with the questions, you will encounter a formula just like this one here, which is called the impulse momentum theorem formula. Then you can manipulate this formula to be like this: F net is equal to change in P over change in T. Now, also this formula here can help you to remind yourself of the definition of Newton's second law in terms of momentum, to say that net force is the rate of change of momentum. Remember, if something is over change in time, we just say is the rate. So we say the net force of an object is equal to the rate of change of momentum of the object in the direction of the net force. So having to write that formula like that can help you to recall the definition for Newton's second law in terms of momentum. Then we have impulse. Impulse is the product of the net force acting on an object and the time the net force acts on the object. So again, with this one, we have the formula for impulse is equal to F net and then delta T. So if you can look at this, you can see that impulse is the product of the net force and the change in time. So they say impulse is the product of the net force acting on an object and the time the net force acts on the object. So also having to write this formula here can help you to recall the definition for impulse, right? So you can see how closely related these definitions are to the formulas. We have isolated system. It says this is a system on which the net external force is zero, right? So it's just like that, as simple as that. And then let's go to principle of conservation of linear momentum. So this is one of the definitions that you should really know by heart, because it's definitely coming in your exam. The total linear momentum of an isolated system remains constant. So it's just like that. You put it like that. Principle of conservation of linear momentum simply states that in an isolated system, the total linear momentum is conserved. Right. Then let's look at these two last definition: elastic collision and inelastic collision. So an elastic collision, we say this is a collision for which the total kinetic energy remains constant. So in other words, here there is no loss of kinetic energy, right? So with this one, it is very important to note that no loss of kinetic energy here. No loss of kinetic energy. Then we have an inelastic collision. We say this is a collision in which some kinetic energy is lost. So here there is loss of kinetic energy. But then it is very important to note that in both these collisions, momentum is conserved, right? So if you have looked at your notes already, you know what I'm talking about. So momentum is conserved. So for both these collisions, we say momentum is conserved, but then we just will understand the concept as we go along tackling the questions. Now let's get right down to the business of the day, which is, with me, it's all about tackling those practice exam papers, and then we escalate to past exam papers, because it's all about harnessing that skill of approaching exam papers, and then just making sure that you are less anxious when it comes to answering exam papers, because the point of all this is for you to gain confidence in answering that paper so that you get yourself some decent looking marks. Right. So let's not waste any further time. We have question 1 here. It says a ball with a mass of 250 grams is thrown at a wall with a velocity of 5 meters per second. Then 1.1 here says define the term momentum in weights. So you just go P is equals to M times V, and then immediately you remember that momentum is the product of the mass of the object and its velocity, right? So you just go ahead and write that definition there. So we say momentum is the product of the object mass and its velocity, and then you are done. So in an exam situation, you already have 2 marks for that. Then 1.2 says calculate the momentum of the ball, right? So to calculate the momentum of the ball, we have P is equals to M times V, but then it is very crucial to note something here. Our mass here is given in grams, but then we know in physical sciences paper 1, our mass should always be given in kilograms. Note that when we are dealing with paper 1, which is mechanics, our mass should always be in kilograms. But when we are dealing with paper 2, chemistry, our mass should be in grams. Note this about physical sciences. And then we have P is equals to M, our mass here. We have 250 divided by 1000. This will give us 0.25 kg. And then this is 0.25. And then multiplied by V, our V is 5 there. So if you multiply this, we get 1.25 kg meters per second. So if you're wondering where I take this SI unit, note that our mass is given in kgs and our velocity is given in meters per second. So remember, we are multiplying these two. So our resulting SI unit should be a combination of these 2 SI units, right? So just like that, we have our solution. Then let's move to question number 2. Question 2 says a ball is thrown vertically upwards and is allowed to free fall, right? So when we get to VPM, you will understand this term free fall, but then to just tell you the definition, free fall is the motion whereby the only force that an object will experience is the force of gravity. So that means no other force is experienced by the ball besides the force of gravity. Hence, they tell us to ignore the effect of air friction. Now, they say draw a momentum versus time graph to show that motion. So if we are to indicate the trajectory of the ball, we do understand that if it is thrown, let's say maybe it was thrown from the ground, then the ball will just move like this, and then up until it reaches a certain maximum height, and then come back to the initial position in which it was thrown, right? So we are supposed to indicate the momentum of the ball versus time of this trajectory here. So to do that, the first thing that we need to do, obviously, is to draw our Cartesian plane, because this is a graph, and then there we go. Now we consider that our independent variable in this case will be time. Our time is given in seconds, and then our dependent variable will be momentum, which is given in kg meters per second, right? Now we do understand that as the ball is thrown vertically upward, what will happen to its kinetic energy? When an object is thrown vertically upward, its kinetic energy decreases, right? So the kinetic energy decreases. Why? Because the velocity decreases as well. So if, for example, we were to throw this ball at a velocity of 10 meters per second, then at the maximum height, we would find that the velocity is now 0 meters per second, which is the point whereby the ball will now have to return back to the ground, right? So we do understand that as the object is moving upward, its velocity keeps on decreasing. So if its velocity is decreasing, let's relate that to momentum. Remember, this is not a velocity versus time graph. It is a momentum versus time graph. But then there is a direct proportion relationship between velocity and momentum if we decide to keep the mass constant. So we do understand that during the action of throwing the ball vertically upward and then it comes back down to the ground, the mass is not affected, right? So the mass remains constant. Then if our velocity as the ball is going upward is decreasing, that means even our momentum is decreasing as well, right? And then when it reaches that maximum height and now it has to come back down, what happens as the ball is coming back down? What happens to the kinetic energy? The kinetic energy increases because as the ball is coming back down, the velocity increases, right? So the velocity increases, which means the momentum increases as well, again for a constant mass. So we do understand what is happening here. Now, to indicate that in our graph, this is what we will do. So we understand that what is happening to our to the momentum of the ball as the ball is thrown vertically upward, we do understand that the momentum is decreasing, right, up until it reaches a maximum height. And then after reaching that maximum height, now we see the momentum of the ball increases again, right? But then this time it's increasing in the negative direction since it's now coming back in an opposite direction. So it was thrown vertically upward, but after it reaches a maximum height, it now comes back down. Hence, we see our graph here is now crossing the x-axis and going to the negative direction, right? So this is not to tell you that the ball is going like that. No, this is to tell you that the momentum is decreasing as the ball is going upward. So we would indicate this. So above the x-axis, this indicates that the ball is still upward, right? And then as the ball is still upward, the momentum decreases. But then below the x-axis, this tells you that we are now going downward. And then what happens downward? The momentum of the ball increases, right? So it is increasing in the negative direction. So this value here and that value there is are equal, right? Since this object here is free falling. So if it's free falling, we say the initial momentum in which it was thrown at will be the final momentum in which it arrives back on the initial position in which it was thrown at. So this is how you indicate the momentum versus time graph. So you would then go here and just say this is the momentum versus time graph. And this is how you would indicate that. Question 3, it says a ball with a mass of 250 grams. So once again, we can note that our mass there is given in grams. We need it in kgs. So one thing that you want to do, guys, when you are tackling your exams is that the moment you see that something is not in the desired SI unit, do not wait and to come back and reread the statement when you're about to answer the questions. Just change it right away. Right, so you can see that this is 250 grams. We need it in kgs. Before you can even read the whole statement, just change that to the desired SI unit. So we have 0.25 kg. Then we can continue with the statement is thrown against the wall with a velocity of 20 meters per second. So it's thrown against the wall. That means we are given VI here. This is our initial velocity. The ball bounces back straight with a velocity of 18 meters per second. So this is our VF. Now 3.1 here says explain why this is not an elastic collision. Now remember, with an elastic collision, we say there is no loss of kinetic energy, right? So no loss of kinetic energy. Now, but when we are looking at our VI and VF, we can see that when the ball bounced back, it no longer bounced back with the same velocity in which it hit the wall with, right? So this means that there was a loss of kinetic energy because remember, EK is equal to half mv squared, right? So if we notice a decrease in the velocity, that means this results in a decrease in the kinetic energy, because remember, once again, our mass in this situation remains constant. So when the ball hits against the wall, it does not change the mass. So that means the only thing directly affecting our kinetic energy here is the velocity. So now, because we can see that the velocity decreased upon its impact with the wall, that means the kinetic energy then decreased, right? So this is the reason why this is not elastic. So how do we put it? We say there is a difference in the VI and VF, right, upon impact. And then which indicates that there was a loss in kinetic energy. Which indicates that there was a loss in kinetic energy. Now, we know that a loss in kinetic energy means that this is inelastic, means that the collision was inelastic. So we just mainly say there's a difference in the V initial and the VF upon impact, which indicates that there was a loss in kinetic energy. So this means we have an inelastic collision, right? So that means, in other words, if we had this being thrown against the wall at a velocity of 20 meters per second, and then if it hits the wall, comes back again with a velocity of 20 meters per second, we would say the collision is elastic, because at that point, we wouldn't witness a change in the velocity. We wouldn't witness a decrease in the velocity. The velocity will just remain the same. But then, because here there is a decrease in velocity, it tells us that there is loss of kinetic energy. So I hope that makes sense. Then 3.2 says calculate the change in momentum of the ball as a result of the force that the wall exerts on the ball during the collision. So for this one, let's try to draw the scenario here. So initially we had a ball going that direction. So we'll just assume that it was thrown to the right. Then at a velocity of 20 meters per second, now it hits against the wall and comes back at a velocity of 18 meters per second. The formula that we are supposed to use to calculate the change in momentum goes as change in P is equals to mvf minus vi. So you will definitely see this formula at the back of your formula sheet. Sometimes it is written like this, mvf minus mvi. So when I write it like this, I just factor out the m, because the mass will not change during the impact, right? So we have our mass, it's 0.25 gram, right? But then I want you to note something here. This was thrown, let's say it was thrown to the right at a velocity of 20 meters per second, and then it bounces on the wall and comes back at a velocity of 18 meters per second. Now, the mistake that usually a lot of you make is that you take this 18 as it is, you substitute it to the VF, and then you say minus 20. This is incorrect. Why? Because now note that the 18 meters per second is no longer in the same direction as this one. So this is the point whereby you need to indicate the directions. So the 20 meters per second to the right will give it a positive, will assign it a positive. Then the 18 meters per second, after it bounces against the wall, we will assign it a negative direction. Why? Because it is against the initial direction of motion. It's no longer in the same direction. So we need to indicate it using this, right? Because remember, we are dealing with velocity, and velocity is a vector. It has both magnitude and direction. So at this point, this is where you come here and say 0.25. Then your VF is not just 18, it's negative 18. Then you say minus 20. Then at this point, you can punch all this in your calculator. So note that negative 9.5 kg meters per second. But then because this is physics and we don't leave our answers as negatives here, then we just go change in P is equals to 9.5 kg meters per second. Remember, we are supposed to explain what this negative means. So this negative means that our ball is going to the left or in the opposite direction of motion. Right. Then just like that, you have calculated the change in momentum of the ball. Right. Then let's proceed to question number 4. Now, question 4 says a ball with a mass of 100 gram, right? So again, we can see that it is not in the desired SI unit. So you need to say 100 divided by 1000, and then it gives you 0.1 kg. Right. Then collides against the wall with a velocity of 20 meters per second. The change in momentum of the ball is negative 4 kg meters per second. Now 4.1 says calculate the velocity with which the ball bounces away from the wall. So again, we have the formula change in P is equals to M VF minus VI. But this time around, we are given the change in momentum. So you can see the change in momentum of the ball is negative 4 kg meters per second. So we have negative 4 here. Our mass is 0.1. And then what is our VF? We are not told. Then they just say a ball with a mass of 1,000 gram collides against a wall with a velocity of 20 meters per second. So this is our VI. Now they say calculate the velocity with which the ball bounces away. So this is definitely our VF, right? So we have VF here minus 20. So we can see that it is given as a positive. We have this minus here, so we just substitute it as 20. Now we have VF here minus 20. So we can see that it is given as a positive. We have this minus here, so we just substitute it as 20. Now, to quickly deal with this one, you don't want to do this. You don't want to say 0.1 times VF and 0.1 times that. What you can do is just divide both sides by this 0.1. So that's being smart with your maths. Then that's negative 40 is equals to VF minus 20. You can take this 20 over to that side. That's it will give you negative 20. So if you say negative 40 plus 20, then you get negative 20. So we have VF is equals to negative 20 meters per second, which this would be 20 meters per second. And then since it's negative, that means it's going where? To the left, right? So left. So you can either say left or west. Remember, sometimes you might be given the cardinal points. In fact, most of the time in your exam papers, you are given the cardinal points here. So if it's going to the left, if it's negative, that's west. If it's positive, then that's east, right? Then that's 20 meters per second, west or left, right? Then let's then see here, we have 4.2. It says calculate the force that the ball experiences during the collision. Now, note this, our VF is 20 meters per second. Our VI is 20 meters per second. Now, what does this tell you? It tells you that we are dealing with an elastic collision. Right. So this is an elastic collision, and then that means there was no loss of kinetic energy. No loss of kinetic energy. If there is no loss of kinetic energy, in other words, that means our change in EK would be equals to 0 joules. Right. But then if our change in EK is equals to 0 joules, that is a result of the VI being equals to the VF, right? That means our change in V is also equals to 0 meters per second, right? Now, if our change in V is equals to 0 meters per second, what about our acceleration? Our acceleration is change in V over change in T, which means if this is 0, also our acceleration is 0 meters per second square. Right. Now, why am I talking about all this? I'm heading somewhere here. Remember, I've just concluded that change in EK is 0 joules. And then if we have change in EK is 0 joules, then that means our change in V is 0 meters per second. And then if our change in V is 0 meters per second, our acceleration is also 0 meters per second square. But then remember, we are to calculate the force, right? So the force, according to Newton's second law, is F net is equals to M times A. So the mass times the acceleration of the object. Now, the acceleration we just said is 0. So that means our F net is equals to the mass is 0.1 multiplied by 0. So that means our F net is also 0 newtons, right? So that's how you were just supposed to show that. So note that if our collision is elastic, then there is no loss of kinetic energy, meaning that the force there will be balanced, right? So if the forces are balanced, that means the ball there would experience a zero net force. Now, question 5 says ball A with a mass of 250 grams moves to the right with a velocity of 8 meters per second. It collides with ball B, which is moving at 12 meters per second to the left, right? So it is very crucial here that we take note of the directions, right? So a mass of 250 grams, right away, we divide this by 1,000, and then we'll have 0.25 kg. Moves to the right. So right is positive with a velocity of 8 meters per second. So this would be positive 8 meters per second. It collides with a ball which is moving at 12 meters per second to the left. Left, we assign it a negative. So that means this 12 here should be negative 12, right? So ball B also has a mass of 250 grams, which is 0.25 kg. And then after the collision, ball B continues to move to the left at 1 meters per second. So we know we want to write it as negative 1. While ball A moves at 3 meters per second to the left, it's a negative. So we're going to write this one as negative 3. So you can see that. Now, 5.1 says use calculations to determine if this was an elastic collision or inelastic collision. Now, this is how you perform that calculation, guys. All you need to do here is to compare the sum of the kinetic energy initially to the sum of the kinetic energy finally, right? If you find that the two are equal, then your collision is elastic. If you find that the two are not equal, then your collision is inelastic. As simple as that. Now, let's go about that calculation. So number 1, we'll say sum. So we write the sigma notation here, which means sum. So sum of EKI, so sum of kinetic energy initially. So that's half mv squared of ball A plus half mv squared of ball B, right? Then remember with this one, because it's EK initially, we're just going to go ahead and substitute the initial velocities. Then this is 0.25. Our initial velocity for A was 8. So we have 8 square plus half. Again, the mass is 0.25 because they have the same mass. And then our velocity for B initially, they said it's 12, but then it's going to the left. So that's negative 12. And then square. Now, if we punch all that in the calculator, so let's do that quick. So we have a energy, kinetic energy of 26 joules. Sum of kinetic energy initially is 26 joules, right? Now, after we have that, let's calculate the sum of EK finally. So we have half mv squared of A plus half mv square of B, right? Then let's go ahead substituting the final velocities. So this is half our mass. Remember, during the impact, there is no loss in mass or no change in mass. Then VA, finally, that's negative 1. So we have negative 1 square. Then half 0.25. Here we have negative 3 and then square. Now, one thing you don't want to forget are this square here. So most of the time you can complicate it with the one that we have for momentum. So always double check that you have included that square here, because then if we punch all that in our calculator, so this gives us a value of 1.25 joules, right? Now looking at this, we can tell that obviously here, this collision is inelastic because there was a loss of kinetic energy. So we're just going to go ahead and say, therefore, collision is inelastic. The collision is inelastic. Why? Because the sum of EK initially is actually greater than the sum of EK final. Right. So because we can see that the EK initial is greater than that, that means there was a loss of kinetic energy. Now you can just even go ahead and calculate the energy that was lost. So we lost about 24.75 joules worth of kinetic energy. So we know that this kinetic energy was not just destroyed, it was converted from one form to another, right? So yeah. Then 5.2 says use calculation to determine if momentum was conserved. Now remember I explained there that whether a collision is inelastic or elastic, the momentum will always be conserved. Right, so it's just a matter of using our calculation now to prove that. Now to use the calculation, we can start by calculating the sum of momentum initially. So this would be M1 V1 of A plus M2 V2, that's B, right, initial. Then what is our mass? Our mass is 0.25. Then our velocity again is 8. And then we have mass number 2, that's 0.25 as well. And then velocity of B, remember it's negative 12. Now you want to punch this in your calculator. So we have 0.25 multiplied by 8 plus 0.25 multiplied by negative 12. So this gives us negative 1, right? So we have negative 1 kg meters per second. So this is the sum of the momentum initial, right? Now let's calculate the sum of the momentum finally. So we have, let's do it this side here. Sum of momentum finally, that's M1 V1 of A plus M2 V2, and then we have B. So our mass number 1 is, that is of A, that's 0.25, but then our velocity finally, that's negative 1, then plus 0.25 multiplied by negative 3 this time. Now, if we calculate this one, we also receive negative 1 kg meters per second. Now, looking at this, we can see that the sum of momentum initially is equals to the sum of momentum final. Now, this proves that our momentum is conserved. So we can say, therefore, momentum is conserved. Now, it was just a matter of verifying it with our calculation. But conceptually, we know that whether it was elastic or inelastic, the momentum will forever remain conserved. Now, question 6 says a ball of mass or 0.1 kg. A ball of mass 0.1 kg is thrown at a velocity of 10 meters per second. So this is in the correct SI unit, kg, and then thrown at a velocity of 10 meters per second, direction west. So if our direction is west, west is on the left-hand side, so we can just assign it a negative, and then here we have east, so on the right-hand side, it's a positive. Right. Then against the wall, the ball bounces back at 5 meters per second, direction east. So we can say this one is positive and this one here would be negative. Now 6.1 says calculate the change in momentum that the ball experiences during the collision with the wall. Right. So once again, we are asked to calculate the change in momentum. So the formula for that, that's change in P is equals to M VF minus VI. Right. So what is our mass? Our mass is 0.1. Then the VF, note, direction east. So I'm going to write it as a positive. That's 5. And then this one, direction west, it's a negative. We have minus here, and then we have this negative. So negative multiplied by negative would be positive. So we have plus 10 here. Note these signs. Then that's 0.1 multiplied by 15. So this would give us 1.5 kg meters per second. And since this is a vector, we need to show the direction also. So this is east because it came out as a positive. Right. So done with that one. Then 6.2 says calculate the net force exerted by the wall on the ball during the collision if the collision lasted 0.1 seconds. Right. So let me just erase here. Then to calculate the net force, remember, this is on, if they tell you about the net force and they also tell you the time, note that this is on impulse. So the only quantity here that speaks of the net force and the time is the impulse. So remember, we have impulse is F net delta T, right? But then just above here, we've calculated the change in momentum, and we know about the impulse momentum theorem. So we have the impulse momentum theorem, which simply states that the impulse of the object is equal to the object's change in momentum. So that means the impulse is equal to the object's change in momentum. There we go with the formula. So this is where we get that formula from the impulse momentum theorem, right? Or theorem. Then this is F net is equals to change in P over change in T, right? So we just calculated the change in P here, so that means we can just go 1.5, and then our delta T is 0.1, right? So if you just go 1.5 divided by 0.1, that should give you 15, right? So that's 15 newtons, and then to which direction? East. Because also your net force is a vector. It must have both magnitude and direction. So that's how you use that formula there. Okay, so and this is where we're going to end with our lesson. Make sure that you press the thumbs up button if you have found this lesson helpful. And then also don't forget to share the link with your friends and classmates so that they may also find assistance. With all that being said, let's just call it a day.